Imagine the vacuum of space. It seems empty, still. But what if this emptiness teems with activity, a microscopic frenzy hidden from our view? This is the essence of quantum foam, a concept that redefines the very fabric of our universe. At the smallest scale, space-time, once thought smooth and continuous, dissolves into a chaotic sea of quantum fluctuations. Virtual particles, governed by the strange laws of quantum mechanics, constantly flicker in and out of existence, creating a seething, ever-changing landscape. This is not science fiction. It is a profound implication of the laws of physics as we understand them. Quantum foam challenges our classical intuitions, forcing us to confront the bizarre reality that may lie hidden beneath the surface of our everyday world. The concept of quantum foam emerged from the fertile mind of physicist John Wheeler in the mid-20th century. Wheeler, a giant in the field of general relativity and a mentor to Richard Feynman, was grappling with the implications of combining quantum mechanics with Einstein's theory of gravity. He realized that these two pillars of modern physics, when pushed to their limits, painted a radically different picture of spacetime. According to quantum mechanics, even a vacuum, completely devoid of matter and energy, is not truly empty. Instead, it is filled with virtual particles, fleeting fluctuations of energy that borrow energy from the vacuum, pop into existence, and then quickly annihilate each other, returning their borrowed energy. Wheeler reasoned that these quantum fluctuations, occurring everywhere and at all times, would imbue the fabric of spacetime itself with a kind of quantum fuzziness, a foam-like structure at the smallest scales. If spacetime is indeed a seething sea of quantum foam, how can we detect it? Directly observing something so small and ephemeral seems impossible. However, physicists have devised clever experiments to indirectly probe the nature of the quantum vacuum and search for telltale signs of the foam. One such experiment, the Casimir effect, has provided some of the most compelling evidence for the reality of virtual particles. In this experiment, two perfectly smooth metal plates are placed very close together in a vacuum. Surprisingly, a measurable force arises, pushing the plates together. This force, physicists believe, is due to the virtual particles that constantly pop in and out of existence in the vacuum. Another line of evidence comes from high-precision experiments that study the magnetic properties of particles like muons and electrons. These experiments have revealed tiny discrepancies between theoretical predictions and experimental results, discrepancies that can be explained by taking into account the effects of virtual particles. Section 4. Sizing up the foam, Planck length, and cosmic observations. If spacetime is indeed foamy, how foamy is it? This question has intrigued physicists and cosmologists for decades, leading to numerous theories and models attempting to describe the fundamental nature of our universe. Physicists believe that the characteristic scale of quantum foam is set by the Planck length, an incredibly small distance of about 10 to the minus 35th meters. To put this into perspective, the Planck length is to a meter what a meter is to the observable universe. It's a scale so minuscule that it defies our everyday experiences and challenges our understanding of space and time. This is the scale at which the quantum nature of gravity is expected to become important, and where our current understanding of physics breaks down. At the Planck length, the smooth fabric of spacetime is thought to dissolve into a frothy, turbulent sea of quantum fluctuations where the classical concepts of space and time cease to exist. Some theoretical models suggest that the foam might be less fine and have larger bubbles. These models propose that the quantum foam could vary in texture, with some regions being more turbulent than others, potentially leading to observable effects on a cosmic scale. However, observations of distant quasars, incredibly bright objects powered by supermassive black holes, have placed stringent limits on the size of these hypothetical fluctuations. Quasars serve as natural cosmic beacons, allowing astronomers to probe the structure of spacetime over vast distances. If the foam were too coarse, it would scatter light from these distant sources, blurring their images. The scattering effect would be similar to looking through frosted glass, where the fine details of the objects behind it become obscured. The fact that we observe sharp images of quasars even from billions of light-years away suggests that the fluctuations of quantum foam, if they exist, must be extremely small, perhaps even as small as the Planck length. This remarkable observation provides a crucial constraint on the nature of quantum foam, guiding physicists in their quest to understand the fundamental structure of the universe. Section 5. quantum foam's extended family, vacuum energy, and spin foam. In this section, we delve deeper into the fascinating and complex world of quantum foam and its extended family, exploring the profound implications these concepts have for our understanding of the universe. The concept of quantum foam has profound implications for our understanding of the universe and its evolution. Quantum foam, also known as spacetime foam, is a concept in quantum mechanics that suggests spacetime is not smooth but rather frothy and turbulent at extremely small scales. One of the most intriguing connections is to the mystery of vacuum energy, also known as dark energy. This mysterious form of energy is thought to permeate all of space and is responsible for the accelerated expansion of the universe. This mysterious energy, which makes up about 70% of the energy density of the universe, is causing the expansion of the universe to accelerate. The discovery of dark energy has revolutionized our understanding of cosmology and the fate of the universe. While the exact nature of vacuum energy remains unknown, physicists believe that it may be related to the energy of the quantum vacuum, the seething sea of virtual particles that gives rise to quantum foam. These virtual particles pop in and out of existence, creating a dynamic and ever-changing landscape at the quantum level. Another intriguing connection is to spin foam theory, an approach to quantum gravity that attempts to describe spacetime itself in terms of quantum fluctuations. Spin foam theory is a framework that seeks to unify general relativity and quantum mechanics, two pillars of modern physics that are currently incompatible. In spin foam theory, spacetime is not a continuous background but emerges from a network of interconnected spins representing the fundamental building blocks of space and time. These spins can be thought of as tiny, discrete units that interact with each other to form the fabric of spacetime. These spins fluctuate and interact, giving rise to the dynamic, foam-like structure of spacetime at the Planck scale. At this incredibly small scale, spacetime is no longer smooth and continuous, but is instead a frothy, ever-changing entity, constantly in flux due to the interactions of these fundamental units. This dynamic nature of spacetime at the Planck scale challenges our classical understanding of the universe and opens up new possibilities for exploring the fundamental nature of reality. Section 6. Conclusion: a frontier of cosmic mystery. Quantum foam remains one of the most perplexing and fascinating concepts in modern physics. This idea, first proposed by John Wheeler, suggests that at the smallest scales, space and time are not smooth and continuous but rather frothy and turbulent, much like the surface of a boiling pot of water. These fluctuations occur at the Planck scale, where the effects of quantum mechanics and general relativity intersect. It challenges our classical intuitions about the nature of space and time, suggesting that at the most fundamental level, the universe is a far stranger and more dynamic place than we ever imagined. The very fabric of reality is constantly in flux, with particles popping in and out of existence, creating a seething, ever-changing landscape. While direct experimental evidence for quantum foam is still lacking, a number of indirect observations, such as the Casimir effect and high-precision particle physics experiments, provide tantalizing hints of its existence. The Casimir effect, for instance, demonstrates how quantum fluctuations can produce measurable forces between objects, even in a vacuum. Furthermore, the concept of quantum foam has profound connections to other areas of physics, such as vacuum energy and quantum gravity, offering potential insights into some of the biggest mysteries of the universe. Vacuum energy, the underlying energy present in space even when devoid of matter, is thought to be a manifestation of these quantum fluctuations. Quantum gravity, on the other hand, seeks to unify general relativity and quantum mechanics, and understanding quantum foam could be a crucial step in this quest. The quest to understand quantum foam and its implications is a journey to the very edge of our understanding of the cosmos, a frontier where the familiar laws of physics break down and where the true nature of reality may be far stranger and more wondrous than we ever dared to imagine. As we continue to explore this enigmatic concept, we may uncover new principles that could revolutionize our understanding of the universe, opening up possibilities we have yet to even dream of.